So good morning. So I will introduce the StarPU task-based programming runtime. Um, the idea is that I will show the API. Really, we have seen the principles of StarPU the other day, and now we can look at the exact API, C API. So the first part will be on the basic principles, and we will see more advanced optimizations in the second part. So let's take an example. We have a vector that we have allocated on the stack, for instance, and we have a factor, and we want to scale the vector by the provided factor. So initially, you only have some source code which fills the vector with some values, for instance. So we have this. Now, what you want to do is to first provide this data to StarPU and then run a task that will do the scaling. So what you will need is virtual data, as I mentioned the other day. So what we call a vector, a data handle. So we call this a vector handle. And we call a function that registers the piece of data, so the vector here, and we get as a result the vector handle. So this is a value that is returned to the program after providing the vector, the number of elements, and the size of each element. So from this on, the application is not supposed to use this data anymore, because StarPU is in charge of where the data is. Is it on a GPU? Is it somewhere else on the disk or whatever? So it's not, the program itself is not allowed to access the vector array and only manipulate the vector handle through StarPU to modify the data. So for instance, one can insert a task which is doing some scaling of the vector, telling that yes, we will read and write the vector. So we modify the vector and provide a small factor for the task to execute it. And then we can wait for the task, because this call is asynchronous. So at this point, we are not waiting for the task yet. It's just going on asynchronously. And then we can wait for it and eventually unregister the vector handle. And from then on, the value which is in the array here can be looked at, displayed, etc., because it is not the responsibility of the runtime anymore where the data is. Okay, so that was a quick overview of what submitting a task after registering the data is. Let's see the details. So first, some terminology. So codelet, task, and data handle are the three main words that we will use in this morning. So first, the codelet. So that's basically a new word mostly. So for us, a codelet is just a notion of what kind of function you will do, which kind of computation you will do. So you have several implementations, for instance, of the vector scaling, a CPU1, a GPU1, an FPGA1, or even several implementations with different kinds of compromises. And you gather them into what we call a codelet, which simply lists the implementation. And then the codelet can be used to instantiate tasks. So basically, the codelet provides the information, the common information of the different tasks. So which kind of data does it take? Which are the pointers to the implementations of the task? So the codelet here gathers the implementations, and from there we can create different tasks. So we have two tasks here which perform the same kernel, because the kernel is described by the codelet. Okay, so now a task, that's a more common word. For us, it is an instantiation of a codelet. So it does compute something, some function. And what's interesting in the task is that it takes some input and produces some output, and it executes automatically, so from beginning to end, without getting interrupted. So we have the Kotlin that we have seen before, and then we plug. We know that the Kotlin can take some data as read and write, for instance, for the scalar, for the vector scaling, and then we instantiate a task which takes the data as an input and then computes the result and then emits the data output. So the data itself is a piece of data managed by StarPU. So it can be of different types. That can be a vector, that can be a matrix, that can be a lot of different types. And this is what we give as input and output for a task. I mean, input and output that is managed by StarPU, in that it is kept in memory, it is managed really by StarPU. So the API is basically around these three notions. So declaring a Kotlin that can be quite often static in the program because your implementations are known statically at compile time. Then declaring the data at runtime, saying these are the data size and the storage area for the data. Then you have your function, the kernel function, and you can mix all together to get to submit a task and then wait for it. So let's look at the details, the programming details. So the Kotlin, which gathers the implementations, is simply a structure. So you have, for instance, CPU implementation for the Kotlin. So you just provide it in a CPU func field. Then you tell about the data. You say that you have one piece of data, and you say that it is used as both an input and output. So it is in place modifications actually, since it takes it both as read and write mode. So the task will get just one parameter, and it is allowed to read it and to write to it. But then you may have different. Sorry, and so let's look at the data itself. So you have your vector, and you have the source code to fill the vector, and then you want to register it. So you have the register call which you've seen, and so from now on, you're only supposed to use vector handle. So you can do whatever you want, submitting tasks. You can acquire, and we will see that later. You can submit a lot of tasks on the vector, and then eventually you can unregister the data. So the vector handle is destroyed. So you can, if you want to reuse the vector, you have to register again. So usually you do this at the very end of the application, just before maybe freeing the vector. Now with the kernel themselves, so the function that was referenced from the Kotlin, since it's C, it has to have the same prototype for all kinds of computation. That's a bit of a pity that you don't have polymorphism in C, but okay, StarPU is a C library which allows for a lot of flexibility of integration in different kinds of languages. So we have to go through this. So we have two parameters, buffers, which will be the data of the task, and CLRX, which is the small data, some data that is not managed by StarPU. We will see later. So first, we get the first data of the task. So we access the first element of this array. So it's a void star array because we don't know yet which kind of data this is. And so we cast this into a vector interface and to say this is actually a vector. I know this because that's how I wrote my program. And then I can look at it. So we have some macros here which check for the type of data and check that it is indeed a vector, and then get the attributes of the vector. So the number of elements and a pointer to the vector. So this macro is important, getting the pointer through the provided parameter, because StarPU might have made a copy of the vector, for instance, on a NUMA system. It may not give the pointer to the original location of the data, but to a copy of the data, to make a local copy that can be accessed really efficiently. So the function here, the kernel function, is really not supposed to access some global variables like pointers and everything. It has all the information it needs from the parameters here, so the data, getting the number of elements and the pointer, and also the small factor. So we had a vector scaling example, so we need to know which factor we will use, and that can go through CLarg. So CLarg, we will see that's in the task and that you provide a pointer to the float parameter. And so here you can get it directly without having to register the data, etc. You just get a pointer as you have passed it to the task. And eventually you can do the actual vector scaling. So since you now have the pointer to the data, the number of elements, and then you can simply multiply the vector by the factor that you had set. Okay, so this is basically the kernel function. Then now, how do you submit a task? So we have a function which is called StarPU task insert, which does the submission quite easily. So it does insert the task in the DAG, so the task graph of StarPU, while generating the dependencies as I've described on Monday. So the idea is that you pass several arguments to the function. So first you pass it the address of the codelet structure. So that's here that to tell this task will perform this kind of computation. So here the vector scaling and computation. So now the task knows the different kinds of implementations which are available for this task. Then we provide the vector handle to tell you will work on this vector, and this is some data which is managed by StarPU. It is a data handle. So StarPU knows that it will have to transfer the data maybe on a GPU or something like this. And then it detects from the access mode of the data that this task will have to wait for any previous task which was producing the data, because we want to wait for the result of the previous task that rose to this handle before executing this task. And conversely, since it is writing to the data, then this task will be depending on by further tasks which will want to read this piece of data. And then eventually we have the factor of the vector scaling. So here we provide the address of a small variables and then its size, and say it is a value. So you can pass it not as a registered data, but just some small value that will be copied to the task execution. It's not efficient to always copy, but since it's a small factor, then that's fine. It's less expensive to just pass it like this in line than registering a data and registering, etc. So for small parameters, that's completely fine to do it like this. And eventually, you mark the end of the argument, because you can go on with several handles, several values as much as you want, and then you can just get the end of the argument. So you have to pass 0 to tell StarPU this is the end of arguments. A bit like the exec system call or something like this. You have to put a marker so that C knows that the arguments are over. Okay, so the submission is non-blocking, so it goes quite fast. It's like a few microseconds only to create the task and then submit to the scheduler. And then you can call it again and again and again to submit a lot of tasks like we have seen in the Sholicity case. All of the simulations of tasks will be non-blocking. The dependencies will be computed at the same time. So just looking at the different access modes of the parameters of the tasks. And so StarPU will create a task graph actually while you're submitting the task. So you can do this really dynamically. That is, the tasks are starting to execute as soon as you start submitting them. And then while you're submitting tasks from the main thread, tasks start executing. So you will have a concurrency between the submission and the execution. So the order of the submission follows the submission order of the program with the addition of dependencies. So that's what we call the sequential task flow paradigm. And that is the submission source code looks like a sequential program. You just submit the task one after the other in the order that you would have in a sequential program. But then StarPU determines the parallelism from the data dependencies and executes in parallel whatever can be executed on parallel. So you can submit several tasks like this. This is non-blocking. And eventually you can wait for all the tasks to finish. So possibly like you have submitted all of the tasks of your program, and then you just wait for the computation to complete. So waits for all tasks that had been previously submitted. So getting back to our example, we have all the elements that we have seen before and that are presented initially in the first slide, but here we have the whole example. That is basically what you will look at during the first Hansen session to make sure that you understand each piece, how they connect to each other. Yeah, and have a look at the documentation to check the details maybe. So for instance, the details of the parameters here. Okay, so now we not only have CPUs, but also GPUs. So the idea is to extend the codlet to handle heterogeneity. That is, we want to look at how we can express that we have different implementations on the CPUs and GPUs, and how can you provide the implementation for the GPUs. So first, you can provide several implementations, CPU implementations. So here we had an array, and so the array can be filled with several pointers to several functions. And StarPU will automatically determine which one is fastest for the data size and for the execution system based on previous executions. So when you first run your application, it will measure how fast the different implementations are, and then select at runtime which one is fastest. So here, for instance, we have SSE, AVX, and you can also provide the information whether AVX can be used, for instance, depending on the capacities of the CPUs. Now, for GPUs, you can provide the implementations in some additional fields. So you have OpenCL and CUDA. So you just provide function pointers for these. And then let's look at how they look like. So for CUDA, we still have the same type of function as before, as CPU functions with the buffers and the CLRs. But this is really a CUDA source code. So we have to tell that this is an external C function so that it can be called from StarPU as it is used to. And then we have the same macros here to get from the buffer the number of elements and the pointer. But here, this is a GPU pointer. So at this point, we are getting called as the implementation. At this point, StarPU will have already transferred the data on the GPU. So this is a GPU pointer, and this is not something you can inference from the CPU itself. You will have to pass it to the kernel function of the GPU. And you get the small factor. And this one, however, is a CPU function. It's not managed by StarPU, it's just passed on to the task implementation as it is. So this is CUDA, so you have to compute how many threads per block you want. So for instance, 64 threads per block. And then you look at the number of elements to process, and then you can distribute them to the different blocks. So you have different kinds of different number of blocks depending on the threads per block and the number of elements. And then you can actually call the CUDA implementation on the GPU, passing it on the number of blocks and the number of threads per block. So this is the common parameter passing to specify the kind of parallelization on the GPU. And also you pass something which is really important, is giving the CUDA stream to use to submit the kernel. This is really important because otherwise the default stream, the default CUDA stream brings a lot of synchronization, spurious synchronization with transfers, with data management and everything. So you really want to add this parameter, which doesn't change really anything in the submission, just an additional parameter so that things can go nicely. And then you have the actual implementation, which is simple on CUDA code that just takes the parameters that we have provided. So we have provided the vector and the scaling factor. So you have these, so the pointer inside the GPU memory and the factor, and then you can simply loop over it to multiply actually the vector. So that's it for CUDA. Now OpenCL is the same. I won't go into the details, but you see the structure is roughly the same. So get the pointer, ask StarPU for which kernel queue, and OpenCL program, load the OpenCL program to put it on some queue, then provide the parameters, and then tell us OpenCL, this is the kernel I want to execute, and then we have the kernel. So we have examples in StarPU to show this in details. I wanted to just show the Fortran case for people who need to use Fortran. The principle is really the same. We just have to adapt to the Fortran expressions. So the codelet is an allocatable pointer for Fortran. So we have a function that provides the allocation for this. So once you have your codelet, you can fill the different fields. So the CPU function for it, and the data access modes, so saying that I have a buffer which is accessed in a read-write mode. The implementation itself can be done in Fortran. So like in C, we have the two parameters, and the type of the parameters is always the same, like this. And then you have some functions to get the number of elements and the pointer to the actual data. And so here, this returns the val pointer. So this is a pointer, and you say it is real. And you also specify Fortran that it has n elements. So you had to get the number of elements before this. And about the factors, you can get its content with some unpack arg function call, and then you can do the scaling as usual. So this is for the kernel. And then how do you actually submit a task? So you have your array. So you would use allocatable arrays with the varying size, and then you register to StarPU as for C. So you provide the location of the array, the number of elements, and the size of each element, and you get back a vector handle. So it is a CPTR, so opaque type, but then you can insert the task. You provide the codelet that you had allocated, the access mode, the values of the factor, and the size of the value, and then as usual you terminate the list of factors. So that was basically for Fortran. It's the same principles. So the everything we will see in the tutorial are basically the same in Fortran. The bindings are really similar. So now we have the data interface. I mentioned that we have several kinds of data. So the vector, we've seen that you register telling the pointer, number of elements, and size of elements. But then you have matrix tiles. So it is part of a whole matrix. So we have a big matrix, for instance, or just one small matrix. And what you specify is the pointer and the size, the number of elements in the tile and the size of it, but also here the number of leading elements. So when the tile is part of a big matrix, you may have several elements between each line of the tile. So you have to specify whether it is contiguous in memory or it is indeed part. It is a tile that is part of a bigger matrix. So you have to tell how many elements there is between each line of the tile. And we have a lot of different types of data. So for instance, BCSR matrices. So you have to pass on the indices, the row PTR, the first entry. Depending on the type, you will have to provide different pointers, different size. We have the documentation for all of this. So we have also OOC, sparse matrixing, and etc. And this is extensible. You can provide your own type if you have, I don't know, complex numbers, a tree of data, or different kinds of types. You can actually describe the data to StarPU. The thing is, all you need to express to StarPU is the amount of data that is represented, and maybe several buffers of data, several pieces of data. So for instance, for BCSR, we have several arrays to express, but one matrix, one BCSR matrix tile is one data and several arrays at the same time. But for a task, you just pass on one data. So the way you express is really telling my piece of data is like this, and then to transfer on the GPU, this is how it is done. So we have 3 arrays, for instance, to transfer with this size, and StarPU will handle the rest. The last thing I wanted to discuss this morning is partitioning. So the idea is you have a big matrix and you want to parallelize the computation over the matrix. So when you want to split it in small pieces, so you can adapt the granularity of the tasks depending on the number of pieces that you will get. So what we have is notion of filter, which filters a piece of data. So here we have still our vector, which has been registered, so like we've seen before. And we want to split the vector in several pieces. So we have the function, the filtering function here, that knows how to split a vector. And we tell which number of parts we want. So the number of children data that we will get. And we call data partition that we provide with the handle and the filter. And from now on, the data is partitioned. So you're not supposed to access to the handle here anymore, and only access the data through the sub handles, so the small pieces of the data. So for instance, here, I'm getting the number of children of the handle, and then can access the sub data of the handle, so the sub data number I in my I loop, and then submit a task on the sub handle. So here I have split my vector and run the computation in parallel on each sub handle. So all of the computation then can proceed in parallel since the sub handles here are completely independent. It's a partition of the vector. And eventually, once you have waited for all tasks to complete, you can unpartition the handle and StarPU will collect all the pieces, all the small vectors that maybe have been computed on the GPU or whatever. So it will collect it all back into the original handle. And from then on, you can access the handle as usual. Okay, so that was it for now for submitting a task and partitioning. So we can move on to the hands-on session. I have sent, I believe, the link to the detailed content. So that there was the guide that we have sent previously, but I'm putting in the chat the address of the more detailed tutorial. So it has basically the same instructions at the beginning to explain the first example. Let me show it to you, what it looks like. So this is indeed the website I have passed the a link to. So it explains the basic example. So this is the simple version of the source code, but in the content of the archive that we provide, you will see that it's more detailed. We have more implementations. We have an OpenCL implementation and things like this. But this is basically the ground version of the vector scaling. And we go into detail into the actual calls to the functions and how we pass on the data and everything, and then how to run it, to check that it works, and then play a bit like disabling the CPUs, disabling CUDA so that you only let OpenCL be used, and look at how the implementation goes. And then an exercise is partitioning an example of matrix multiplication with some filters. And we also provide an example, a matrix multiplication example that is more efficient because it is using cuBLAS and CUDA. And then oh no, sorry, the partitioning here, it's not an exercise, it's an example. So an example on matrix multiplication. And then the actual exercise is to split the vector scaling into pieces, like we've seen in the slides, but then we do it again for real and check that it does actually work, that you do get some parallelism that is distributed over the workers. Okay, so one last thing is to execute this, we use the getting started guide section 2. We have the explanations for running a Docker container so that you get all the dependencies. And in particular, you get the simulation dependencies. So this is explained in the here when you build. So you have a make file, so you just have to run make to build at this point, but you will be able to look at the make file how you are supposed to use StarPU, so the compilation flags and things like this. And the important thing is to be able to run the CUDA and OpenCL versions, even if you don't have a CUDA or OpenCL GPU, then you can use simulation. So this call here allows you to enable the simulation version of StarPU. Then you can recompile your example. And then when you run it, it will actually run in simulation, so that when you disable CPUs, you will see that it pushes in the task to the GPU virtually. Of course, the computation don't actually happen because this is simulation, but all of the StarPU runtime will just act like on a real system with a GPU and CPU, all the scheduling and everything. So you will be able to really look at what you get, what kind of statistics of which task went to the CPUs, to the GPUs, etc. Okay, so I see a question in the pad. How is the virtual memory done? How do you manage to transfer the data to the GPU if you need it there? That is completely automatic. So the application doesn't have to tell anything about it. Once it has registered the data and inserted the task, then StarPU knows that it has to transfer the initial value of the data to the GPU and leave the value on the GPU if there is no pressing need for putting it back to the main memory, so that if another task wants to reuse the value constructed by the first task, then it will be able to just execute on the GPU immediately without having to wait for a transfer, because we already have a copy on the GPU. So the application writer really only has to care about registering the data, and then everything happens automatically.